Okay, so thank you, Shubham. Uh, I will share my screen now. Can you s- can you see my screen?
Yes, it's continue.
Okay. So once again, welcome you all to this session of behind the scenes of generative AI. In this, we are going to see first I'm going to explain RNNs and LSTMs, and then Shubham will take on from attentions and transformers. So these the four things that I mentioned now, they are like prerequisites. They are for the basic understanding of how how ChatGPT works and how is the you know how the transformers work. So we are going to first see about RNNs. All right. So RNN stands for recurrent neural networks. The contents, these are the contents which we are going to cover in this session now. So first, for the introduction, let us start with an activity. So think about any sentence you know by heart. For example, the lyrics from your favorite song or a nursery rhyme or anything. Like Jack and Jill went up a hill to fetch a pail of water. Anything. Think about any sentence. Now, like tell it. You can tell it up aloud two or three times. So you can to understand that you know the sentence by heart. Now you try to say the sentence, but in the reverse order. You can you can take a few seconds to try it. You'll find it is extremely difficult to say the sentence in the reverse order, though you have memorized the sentence. Even if you know the alphabet song A B C D E F G, if I tell you to start from Z and go in the reverse order, it will be very difficult for you to do so, isn't it? So this is the concept of sequential memory. Our brains is trained to handle patterns and to remember sequential data. So the lyrics of the songs, even the songs, even any sentences, anything we by heart them as sequential memory. So what are the examples of sequential data? Like for example, words, they are a sequence of letters, and sentences, they are a sequence of words. Similarly, there is speech or audio, which is sequence of smaller audio chunks. And then you have time series data, where you have any data, but it varies with time. All right. So why? What is the main intuition behind RNN? Like, why do you need RNN? You have like normal feed forward networks. Then why do you need RNNs at all? So if you see in this image, we have like a single hidden node over here, and there's an input, there's a hidden layer, and there's an output. And the very basic representation of a recurrent neural network is like there is a self loop, all right, in the hidden state. So what is the self loop? Why is it there, and how is it works? We are going to see all that. So as I mentioned, the concept of internal memory, like what I mentioned earlier was memory. How memory is how our brain is trained to recognize and it stores patterns. So similarly, RNN, it should also be able to remember things. It should have memory capabilities. So if you see over here, what time is it? And then there's a question mark. So first thing, if you want to give this as an input to a neural network, you first thing this sentences, these words, they are not understood by the network. So you need to encode them. You need to like use proper encoding technique and then convert them into a vector and then feed into the network. So this is like a representation of how the network is affected. And this is like what is converted to 0, 1 and time is converted to 0, 2 and so on. And the reason this is sequential is that if I say what time is it, and if I change the order, if I say is it time what, then the meaning changes. Correct. Similarly, like dogs I love and I love dogs. The If you change the order, the meaning changes. That is the importance of sequential data. So if you can see over here, initially it considers what and it stores some part of it as memory. Then it stores time into the memory. then it stores is into the memory. But you see the problem, the information about what gets smaller and smaller. Previous the as you increase, as you go forward, the it has difficulty in retaining the information. So the information about what and time is very less compared to is it and this question mark. So this is the thing about RNNs. It has a short term memory. So what are the like broad types of RNNs? Uh, as you can see over here, there is one-to-one RNN, that is the vanilla RNN. Then there's one-to-many, many-to-one, many-to-many. So if you see, like if there is a single input-output problem, then you have single input as a node, input node, then you have hidden layer, and then you have single output as your output node. Then if you have image caption, then your input would be an image and your output would be a sequence of words. So that is why it is one-to-many. If it is sentiment analysis, then your input would be a sequence of words and your output would be like a single word, like happy, sad, or maybe confused, etc. So that's why it's many to one. Similarly, here in machine translation, like if you are translating word to word. So that's why it's many to many. All right. So I hope everyone is with me so far. Can anybody of you respond if you understood till this part? Is there any problem till here? Okay. I take your silence as no problem.
Yes, yes.
All right. So this is the okay, nice. So this is the RNN architecture. Uh, Here, if you see the only thing you need to know over here. Sorry. Yeah, this is the main. This is the main network, RNN network, and this is the result of unfolding the network. Now, what do I mean by unfolding? As I mentioned earlier, RNN works on sequential data. So what do you do is first consider the example, what time is it? You input what as as xi. Then something happens to it, it gives you an intermediate output, but you're not interested in that. Why? Because you have more data to feed. Then you input time in this. Xi is time. You encode the time and you feed it. Then something happens. Then then you give it, and then you give it question mark. Then after giving it all these sequence of words, then it will try and find the next word which will fit or it will match the sequence. Okay, so this is how this RNN architecture it actually works. And the reason we unfold it like this is for our understanding. In reality, this is the only thing which is present. But for our better understanding, we represented it like this. And now I'll explain what are the terms over here. So if you consider any one single any one single this thing node, this is the repeating module. If you see this module, it gets repeated. And if you notice closely, as I mentioned, this is the thing which is with what we are concerned with, and this is just the unfolding of the network. And if you see the weights, they are the same because like we are not changing them for when we are like going forward. And similarly, this WH is also the same, and WX is also the same. Only the inputs are different at different time instances. I hope you can see over from here. And also, this H0 is called the hidden state, and it acts like a memory. This H0 is the memory component of this RNN. All right. So consider like input from X at t equal to 2. Okay, so this is X2. Say it's like in the case of what time is it? It is time. So this time it is converted to a vector, and then it is multiplied with a WX, a weight matrix. Then it's given into these hidden nodes where it like also considers the HT from the previous state. Here in this case, it is H1. So since this is 2, then the previous state is H1. It will multiply H1, that is your memory, with its corresponding the weight matrix, that is WH. and it will add the two results, and we'll apply activation function on it. So we are going to see that, no need to worry. But this is the overall view. This is the memory, and this memory over here, this is the loop. If you see this thing, if you see this t equal to 1, t equal to 2, it is getting passed. In reality, is getting passed to itself. But when we are unfolding it, you can see like it is getting passed like this. All right. Yeah. So like, how does RNN work? Okay. So what exactly do we do? So like, as I mentioned, multiply WH with HT minus 1. That is the weight matrix of this thing, the hidden state, and multiply the input with its respective matrix and add it and say it's like 80. So this is what happens in the hidden nodes. Then you apply activation function. Here we will use tan h. So tan hyperbolic, if you know, it returns a value between -1 and 1, and it can take any number, any real number. So this is the output from the hidden state. This ht is the memory component. And then how do you predict at time t? So it works like this. If you have only data from t equal to 1 to t equal to 3, then you go like you feed it t1, t equal to 2, t equal to 3, and then you weighted what's the output after this. Then this is your predicted output at t equal to 4. If in case you have only like two instances of data, like t equal to 1 and t equal to 2, then you give it two input sequentially and wait. So this y2 is your predicted like predicted x3. Okay. And here the prediction is given by softmax of this ht multiplied by its respective weight matrix, and the softmax activation function is done. So softmax is nothing but if you have a vector, then it's e raised to x divided by summation of e raised to x for all the x in all the individual x values in the vector. If you don't know, vector is also like a matrix only. Like this, the WH is a D cross D matrix. HT minus 1 is the which is the memory component. It's a D cross 1. That is, it's a column vector. XT is also a column vector. Is the input. K is the dimension of the input vector, and D is the number of hidden nodes. And if you can see this, output is also K cross 1. So this is the matrix operation. So we are going to see with an example how does an RNN work. So consider this word DOG. Consider this word.
Jenson, you're on mute. By mistake, you're on mute, Jenson.
Am I audible?
Yes, continue.
Okay. Yeah. So I'll go a little bit faster since we have very
Share
less
screen.
time. It's not shared.
No, no.
Okay. Is it visible now?
Yes,
Yes,
yes.
it's continue.
Okay, fine. So like we'll take this example where you have to consider this word dog. Like you consider the word dog as a sequence of letters. So you have to predict what's the next letter. So in this case, if you say like dogs, then S makes sense. If you say like doggy, then GIE makes sense. So you have to complete the word. So here we are doing first DOG, we are doing one hot encoding. So as you can see, this is the result of the one hot encoding, because as I mentioned earlier, computers can't understand text, it can only understand numbers. And if you think carefully, at the end of the day, all neural networks are like just doing addition and multiplication of numbers. There is nothing much more to it, but they are arranged in a little bit scary manner. That's why it's a bit difficult to understand. But all they do is addition and multiplication, and maybe they apply functions like tan h or something. So yeah, we'll take this example. And then this is how the like multiplication is done. So the first step is WH into HT minus 1, that is memory, previous memory, and the current input. You add it. So this is what is happening over here. This is the previous memory. This is the current input. and you are multiplying it with its respective weight matrix. Is my pointer visible? And you're getting 80 values. Okay, this is for value. This is for value at a equal to 1. Now you'll apply activation function on it, and it will give you ht values here. Since t is 1, it is h1. And then you first multiply it with wy, and then you apply softmax. Then you have yes, yeah. Then you have this yt as your output. This is the case where the weights initially the weights are randomized. So this h value now one thing to note over here. Here there is h0, but you have not you have just given your input x1. So this, if you don't know something, then what do you take it? You take it as 0. So h0 is a matrix of zeros. And x1 will be a proper matrix which has some memory component, but h0 will be matrix of zero. So that is why this h0 is zeros. And this is the weight matrix, which is initially this is randomized. Then we are going to find the proper weight matrix by using back propagation, but first we are doing my randomized. And then d, for d it is 100. Then it's getting multiplied. You can see the calculations over here, and the final output you can see 0.32, 0.21, 0.24, 0.22. This is the output of softmax. So you can consider this as the as a probability values. So like 0.32 as the highest value. So you can consider this as 100, because it is basically giving you the same. You're giving it a d, and the output is also d. Since you consider this 0.32 as the maximum value, you consider it 1, and you consider the rest as zeros. So initially here it didn't do anything because we used untrained random weights, but now you have to train it. So how will you train it? You will train it using backpropagation through time. When I showed you this architecture, I told you that this is the actual architecture and this is just unfolding it. At different instances of time, this is how it looks. For just a moment, consider these as layers and think of how you'll apply backpropagation to it. So that is the essence of backpropagation through time. So the layout is like, first you initialize the weight matrices randomly. Then you forward like do forward propagation and compute the predictions as we did in this case. We found this. Then you compute the loss. Then you back propagate to compute the gradients with respect to the loss, and update the weights based on the gradients, and you repeat these steps. Repeat these steps for every input data you have. So if you have what time is it? What time is it? You have like 4 instances of data. So you repeat this 4 times. So this is the beauty of RNN networks also. It can take different lengths of data. For example, if you have like stock market prices, say company A has like 10 days, like for data for 10 days, and company B has data for 5 days. You can still use the same RNN network to predict for each of the companies. Because like if you have like data for 10 days, you will repeat 10 times. The same architecture, you'll repeat 10 times. And if it is for 5 days, you'll consider a separate RNN network, and then you'll repeat it five times. In that case, it will work. So this is the thing, back propagation to time. So how does it work? So in our example, we took this DOGS. So we can use multi-class cross entropy function, loss function. So what is it? Is basically this is minus of probability that probability that class belongs to the target into log of the probability of the class belongs in the predicted. So if you see over here in the case of DOGS, this YT is 1 because this is 100. So it actually T for this is YT is 1, and y hat t is 0.32. That is for the first value. And to calculate and similarly, if you do summation, you'll get the losses for all this. This will be 0 into this log of, where is that? Log of 0.21 with that minus sign. So in it, since it's 0 into everything, the rest values will be 0. The only value considered will be this, as you can see over here. And then how do you calculate the total loss? This is a loss for one layer or like one instance, L1, L2, L3. So the total loss is you add all the loss in all the layers, and that is your total loss. Since your data is like sequential, for every layer, every time it is giving you a loss, it will store this loss and it will eventually add it in the forward propagation. In the backward propagation, now it will do something. What it will do? It will do weight updation. So this is the weight updation rule. Like this, your current weight is current weight minus a learning rate times the gradient of the loss function with respect to the this thing same variable wi. So the easy thing is like we have this eta, so we have this learning rate, but now how to compute this gradient? That is the difficulty, which that's the challenge. So this is the explanation for how to calculate the gradient. By the way, till here, does anyone have any doubts or does anyone have to ask anything? You can unmute and ask.
Why didn't we use SVM
Sorry, why didn't you use SVM means like for what? For doing DOGS?
for doing this purpose? Yeah.
So like the example that I took is like you have to do prediction. You have a series, you have a sequence data, and you have to do prediction. So I don't know why would you use SVM in that case, but like once you have a sequential data, you have to predict what's in the next sequence. Then you use RNNs. That's the entire reason why you use RNNs.
Yeah, and to add what Jensen said, so as you asked, SVM does it is trained first on the data that it has, and it then segregates data, basically classifies data,
Yeah,
predicts data, classification regression thing, correct? And
yeah,
doing that, it does that by learning something that it had before. Okay, if I give you an example, suppose I say you a sentence: I live in France, comma, I like to eat Chinese, comma, I can speak dash fluent. Okay, so here you need memory to answer this. Okay, so the answer for this will be Chinese as of now. Okay, Chinese language as of now. If as we are learning RNS, so this thing can't be done using SVMs because they don't have memory factor into it, which will hold the dependencies of the next word that to be predicted on the basis of the words that came in the order. Understood? So the dependencies that were there in the whole sentence on the basis of which we arrived on this answer Chinese, as ChatGPT does. If you search anything on ChatGPT, it writes things word by word, correct? So how that words come is basically the context of the words that it had given before and the thing that you have gave as a prompt to it. Did you got it? Is it out clear?
Yeah.
Yes, okay.
like since like he gave an example, Shubham gave an example. Like I also have an example. Like suppose like the brown and black dog which was playing with the cat was a German Shepherd. Now, if you are asked, like if you have the input as brown black dot, which was playing with the cat, was a dot dot. You have to give two words. So when you give x2, x4, x5, that is brown, black, and dog as the input, these words when you run through the RNN, since it has short-term memory, there's a problem of short-term memory. The knowledge about this brown and black and dog, it's so less that it can't successfully predict that it is German Shepherd. It has more knowledge about cat, the weight, playing, so on so. That's the issue with the uh, like what Shubham also was trying to say. Anyways, we'll return. Like so, how do we calculate the gradients? So I'll keep it as simple as I can. So for calculating gradient, we can use chain rule. So for chain rule, you have to find dependency. So like this LT, this total loss is given by this formula. And in this formula, there is y hat, and y hat is given by softmax of ZT, as you can see over here. This is your y hat of T, which is given by softmax of ZT, and ZT is WI into HT. The varying component over here is weight matrix for Y. So when you apply chain rule, you will find you will get this. And when you like find the gradient, you will find that you have to find it is like you have to do del LT by del WY if you like apply chain rule. So this law, this what say loss, total loss depends on change in uh, the weight matrix for like WY. And similarly for WX also, this was for WY, this is for WX. And there's a issue with the for doing it for WX. If you do it for WH, it will be the same. Like you will get a similar relationship. But like if you do it for WX, there's a recursive loop. Because if you see total loss, it depends on y hat, which depends on ZT, which depends on HT, but HT in turn like depends on WX. So if you come eventually, you will reach WX. So with if you do like then with respect to WX, then you will get there's a dependency on WX itself. So that to like solve that, you have to do recursive chain rule. Like if you see over here, this term, HT upon WX. So you have to expand that term HT upon WX till you do like HT upon HT minus 1 into HT minus 1 upon HT minus 2. All these are the derivatives. And finally, you'll have H1 by del of WX. This is the mathematical part. So this is how the gradient is calculated for X. Here you can see like this is ht upon k, this term. You have to do it like ht upon ht minus 1, then ht minus 1 upon ht minus 2 dot 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 till k equal to 0, till you have to do h0 upon wx. That's where you can terminate, and then you have to do it summation for all terms of t, like for all time instances. So that's your total loss. So this part was a little bit mathematical, but then let's move forward. So the biggest problem with RNN is the vanishing or the exploding gradient problem. So if you see over here, yeah, if you see this term, which I explained, this is H15 by H2. You are computing the gradient, the dependency. This L is dependent on this y hat. This is dependent on this Z15. Z15 is dependent on H15. H15 is dependent on so many things. This is the multiplication of each gradient, H15 by H14 into H14 by H13. So this is the problem with RNN. So how do I explain it easier? Consider a value like 0.5. If you do like 0.5 raised to 20, like if you have like a sequence of 20 inputs, you'll get a value which is very closer to 0. And so that is your gradient is vanishing, which means that when you do back propagation, your initial layers, these layers will learn, but as you as you as you go behind and behind, these the initial layers, they will not learn much. So they will have very few, the information which they have, it will be very less, as you can see from this diagram as well. The information about what is very less, and this is the issue, because once you multiply it, once you back propagate it many lots of times, your gradient becomes so small, it becomes close to 0, and the weights are not getting updated as much. If you like do this like 1 plus something, 1 plus this value, then you will get a value which is like 1 only. It is not, there's not much difference. So since the weights are not getting updated, it's not learning as well. It's not learning efficiently. So that is the problem with RNN. It has a problem. It has, that's why it has short-term memory. Okay, I hope that part is clear. And I also mentioned this, so giving the sentence. That's why if you give like so big input where this brown and black and dog, these inputs, this German Shepherd depends on the information about these inputs. So that is why RNN will have a problem in like in predicting this word German and Shepherd. Okay. Is this like till here everything is clear? How the like this vanishing and exploding gradient? Okay, exploding gradient is one. If you have like any number greater than one, and if you raise it to a big number also, you get a very huge number. Then again, it's a exploding gradient problem. You're updating the weights too much, and you are losing meaningful data. Compared, like if you compare 1.5 and 3325, there's so such a big difference. That's the exploding gradient problem. Okay, till here anybody has any problem, any doubts? I will go faster. So these are the problems with RNN. You can see there is difficulty, as I mentioned, because of this vanishing gradient problem, difficulty in capturing long-term dependency, lack of parallelism, because like you have to give it sequentially. Like if you have a sentence, you have to give every word one at a time. You have to give a word, you have to wait for the output, you have to give next word, you have to wait, you have to give the next word. Sequentially you have to do. There's no parallelism. And then there's difficulty in choosing the right architecture. Like there are variants of RNN as well. And like what I explained was the vanilla RNN, and there are variants of RNN as well. And then there is difficulty in interpreting the output. Like if you give a word and you give the output, then it is difficult to understand how the network is making its predictions. Yeah, this is a very graphical way to understand the biggest problem with RNN. It has memory issues. So I will. One second. I'll share my collab notebook with you all. Second. Okay. I hope you can see my screen. You can see my screen, right?
Yes, yes.
Yeah,
Yes.
yes, Jenson. Yes, Jenson.
Yeah. So this
To the
is
people
the.
here, just saying this to the people here. Understand it is little tedious and difficult to understand the mathematics, but just understand the intuition behind it, what Ireland was doing. So it will be helpful for you all. So
Yeah.
I think that it was clear. Basically, if I give the short summary what Jensen told, if suppose you want to do something like predicting the next word of a sentence using a deep learning model, and you are given an RN thing, what RN will do is he will predict the word on the basis of the word that came before it. Okay, and when the model is doing this, what it will do in RNN is he will look the word that came immediately before it. It will give them much weight, higher weightage to it. Then the lower weightage to the next immediate word that came, and less weightage to next immediate word that came. Okay, so that's the problem that we face with RNN. That problem is solved in tensor in our transformers, and on the basis of that only, this big LLMs model like ChatGPT's work. How you write a small question and they make a whole big answer out of it. So that will look ahead as we go. Yes, Vincent. Continue.
Okay. So this is a collab notebook for like running like vanilla RNN. So in here, almost everything is coded from scratch, so it is easier to understand. And here, what we are doing is like we are giving some data. Like you can give it a file as well. It can read if you uncomment these lines. Here you are giving some data like some really long to text this, maybe not the perfect, but should get you going. So this is like an input data, and it has to comment. It has to predict the next sequence of words, which will make sense. So like there is this RNN list class is defined, and there is a hidden layer. Then first of all, you need like I told you, you need to understand that computers don't understand like text. You need to convert them into vectors, more specifically into numbers. So like you have to do that. Then there is a softmax function, which is like exponential of summation of exponential upon the exponential. And this is the forward. In the forward pass is what's happening, and this is what's happening in the backward pass, and this is how it's computing the loss. And if you see, this is to train it, and this is to predict it. If you see, if I give it like a sequence length of 25, and it has to read the data from from this input which I gave it, which I read it aloud. And when I train it, it starts initially it gives some like nonsensical words, and but it becomes better and better, even if there is still some mistakes in it. Some like words don't make sense, like these doesn't make sense. But since the input data is very less, that's why it has that's why there's nothing much it can say as well. That's also the thing. It doesn't have a lot of variety. So like if you give like what is the if you give it, you have to start with the word get, and you have to predict words. Then And it's like it says like get. It means to say really, but for some reason it is saying te. That is a error in that. So get really long test to test this, maybe not perfect. So get, if you see it initially in the input, get is here. You see get is only here. Some really long text to test this, maybe not perfect, but should get you going. But it has found a way to combine the get with other words so that it can make a sentence, as you can see from the output. So yeah, so this was about vanilla RNN. Here they are doing prediction of words, which is like prediction of the next word, which because the sentence is a sequence of words. So yeah, well, return. Okay, so the next thing which you're going to see is LSTMs, long short-term memory. Let me. Yes. Screen is visible, right?
Yes, yes.
Yes, yes.
So like consider this example. Say you have to do sentiment analysis. You have like a comment, say like amazing, this box of cereal gave me a perfectly balanced breakfast, dot dot dot, and will definitely be buying again. So like if you think as a human, if you want to say ki, you have got this comment about your product, say it's a cereal box, and then you are asked to say like you read this comment, and the next day you are asked to say like what was the comment about. Then you won't be saying ki, like you won't be giving the exact words. You won't say ki, there I got such a customer who said these words, amazing, this box of cereal gave me. You won't remember like that. What you will remember is these keywords. Amazing. He told that it was amazing. It was a perfectly balanced balanced breakfast, and he. So because that's what our brain is doing, it is discarding the redundant information and it's only keeping the essential information. So that's what we want our LSTMs also to do. So by the way, the reason we have LSTMs is because of the problem with this RNN. It has memory issue. It can't remember long-term dependencies. If the sequence is if it is asked to make an inference about a word or a letter which is like way which is given way earlier, then it will have difficulty in doing that. So that is why we have LSTMs. So if you see, this is like an RNN network. This is an unfolded RNN network. So essentially the network, but then you are like unfolding it, and then you are giving it this as the input. Convert these words into the this thing vectors. So this has a vector like 0.1, 0.51. So this is a matrix. This is like a matrix. It's like vector. So this vector is given to this RNN, and similarly this is given to this. This is given to this. Is given to this, and so on. What you can see over here is that this is the input. This is the memory from the previous state, and this is the immediate output. And this is actually the immediate output, or this is the memory for the next state. So this memory is taken here, and given the current input, it is combining. It is using this tanh activation function and giving the memory for this. So it is storing this information, and then sequentially it's giving over to here. Sequentially it's happening. It's taking this information, using this as input, doing some mathematical operation to giving it as a memory of new information, which has all these previous informations. That's what RNNs were doing. LSTMs, they also work similarly, but they don't have the issue of like long-term dependencies. So they can make a reference about long-term dependency as well. So like if you have like the same vector, these vectors are the same. So instead of this architecture, you have this LSTM architecture, which I'm going to explain. It also is very similar. This is an unfolded LSTM architecture. The repeating unit is this unit. Okay, so like it's given over here. This is the okay, so I'll explain from here. So the most important thing to know about this is there is two things to an LSTM. One thing is there's a long-term memory. Second thing, there's a short-term memory. Okay, that is easy to understand. This line over here, which is called the cell state, it represents long-term memory, and this line, it's like this line, it represents short-term memory or hidden state. Okay. So cell state means long-term memory, hidden state means short-term memory. Okay. And the way LSTMs work is like there are various gates which ensure that you don't have this vanishing gradient problem. So to solve the problem of vanishing gradient and or exploding gradient, this LSTM solves it. And this is like architecture. This is a repeating unit. This is repeated like this. And if you can see, this is the input. This is the hidden state. Something is happening over here, which I'm going to explain. So there are 4 interacting layers. There's the one layer, layer 2, layer 3, layer 4. I'm going to explain this. So first thing, as I mentioned, there's a cell state, there's a hidden state, and you're giving input at current time step. So this is the input, this is the hidden state, this is the cell state. Now there are various gates. From here, you can see there are various gates. I'm going to explain these gates in detail, so no need to worry. So this is gates ensures that LSTMs like they work properly. Like this gates is the entire like it is basically this architecture consists of all these gates. So there are like majorly there are 3 gates: forget gate, input gate, and output gate. But then we are going to see the other gates as well. So you can think of these gates as filters. You can think of these gates as filters, and they are like their own neural network. You can think like that. So what are individual gates? So to give you a broad overview, there's a forget gate, there's a learn gate, there's a remember gate, there's an output gate, and that's the gates. Yeah. Okay. So if I the thing is, you have short-term memory over here, you have long-term memory over here, and you have this input over here. So the first thing is, what this forget gate does is, you have some existing memory, you have to remove irrelevant information from it. For example, if you have a sequence of words, you have to remove irrelevant information. So what you need to do is, that's what the forget gate does. So for the work of the forget gate is to remove some amount of irrelevant information. Okay. How it does it is, it uses an sigmoid activation function. So if you know sigmoid activation function, it returns a number between 0 and 1. So it is like a percentage. If you multiply this, the output of the sigmoid with anything, it will give a percentage of the previous value. So what you do is, you consider this previous information and this current information multiplied by the weight matrix, add a bias to it, and give it as an input to the sigmoid. This sigmoid will return a value between 0 and 1, and that you will multiply it with the existing, this is the cell state or the long-term memory. That will denote, if you are multiplying with the value between 0 and 1, obviously it will become reduced. If you are multiplying with 0, it means like the entire long-term information is gone. If you're multiplying it 1, then all the information is preserved. That is, you're not forgetting anything. So this is how the forget gate works. It is forgetting irrelevant information. The next is the learn gate. To now this learn gate is basically you have to adding new information to the memory. So there is 2 parts here. First thing is, you are generating a value between -1 and 1, which is like a memory. And then you're deciding how much percentage of this value you're going to add to your existing memory. Okay. So if you see directly look at this formulas, it becomes like so difficult to understand. But if you think in this perspective, this part over here is generating a value. The CT bar is a value between -1 and 1 because it's output of tan h. And say IT is the value between 0 and 1. So IT is like a percentage value. And it's a similar thing to what happened in the forget gate. This thing is the same as this thing. However, the weights are different. Here there's WI, here there's WF, which means that you have different amounts of information to forget and different amounts to keep. So that is why they are different. But this part is the same. Even here, this part will be the same, which I'm going to tell. So as I like explained in the forget gate also, the same thing you do, take ht minus 1 xt. This is the thing, ht minus 1 xt, give it as an input to the sigmoid by after adding the bias, and you'll get it. And this tan h, you do the same thing, but you multiply it with WC. This is a different weight matrix. Here's a different weight matrix. You add different bias, okay, and the output of tan H will give you CT bar. And by multiplying these two values, if you see this multiply over here, by multiplying these two values, you get the amount of information to add. Okay. So just remember, gate is nothing. It is the addition. This addition part, the output from this learn gate and from this forget gate. This is the like output you're multiplying. This is the percentage of information remembered. Here you're adding it with the your new information you're learning. That is your remember gate. So yeah, that's it, right? Then the last thing about it is output gate. So the output gate is you are modifying your hidden state. That's the output gate. Your cell state is now it's now complete by like forgetting irrelevant information and by adding new information. Your cell state is complete. But now to consider the hidden state, you are doing this process. So the process is like, again, you are finding a value between 0 and 1, 0 to 1 to get a percentage, which you're going to multiply. But this time you are going to take the value from HT. You're going to take the value from cell state, apply tan H on that, which will give you minus value between -1 and 1. And then you multiply this with the percentage. And the resultant would be your HT. Okay, and this HT will be given to the next. It will be given to the next part. As you can see, this is the recurring unit, so repeating unit. So it will be given to the next instance. So yeah, that's the thing. That's the architecture, and that's how LSTM's like it's working using these gates. So there's this forget gate to forget the information, irrelevant information. There's a learn gate to learn new information, and there is this output gate to find the hidden state, to find like what's the short-term memory out of your long-term memory. It's taking your long-term memory as input and doing a bunch of things and giving short-term memory as output. Okay. Then there are lots of variants of LSTMs, like there are peephole LSTMs. If you see the equation here is different, it is considering the cell state values while it is calculating, like while it is getting multiplied with WF. It was not the case over here. So it has the gates will look at the cell state. So that's what's happening over here. The input is this sigmoid gets input from cell state as well. And it has various the output or the like results of various LSTMs are different. So like there are thousands of variants, but like these are the popular variants. Like next is the GRU, which like this GRU is also a little bit special because it is faster than a traditional LSTM because it has less, it involves less tensor operations. Because it combines forget and input gates into a single update gate. So instead of using forget and input gate, it will combine it into a single update gate. And instead of using two states like cell state and hidden state, it uses only one state. That's the hidden state. So it combines both of them. So it is also very popular and also faster. So drawbacks, there's longer training times, large memory requirements, and unable to parallelly train. So this is the drawback of LSTM. Like even here, you have to give the input sequentially. You have to give one word at a time or one letter at a time. That's the difficulty. You can't do parallel train. So this is the conclusion. We have like reached the end here. We have seen this LSTMs and RNNs. We have seen how they work. We saw that architecture. And the next thing beyond this, like the problem with RNN was vanishing gradient problem and that short-term memory issue. So that problem is solved in LSTM. But then you can do something beyond LSTMs also. There is something called attention. And this part Shubham will cover. But before that, I'll show you the link to the this thing. So yeah,
Yeah, Jenson, we will share this by the end of the session, the Cola notebooks
yeah,
with them.
yeah. You can see this notebooks. We'll share these notebooks. Here, what they're doing is that they are using like IMDb movie prediction, and they're using LSTM from that. So we'll be sharing this notebook to you as well. And since we have a lack of time, I won't be explaining this, but I will now hand it over to Shubham.
Hello guys. So hi, I'm Shubham Varma. I am community mentor at SMLRA. So the whole motive of the session was to learn about the new advancement that we are having, the chat GPT things and the bot. Right. So all these things are possible due to one research paper, and that paper was attention is all you need. This paper was done was done by the Google people. So this paper talked about the transformers for the very first time. And since this paper came, the whole field, everything that you see today, the chat GPT, the OpenAI, the OpenAI things, the image things have got a new path to work as they are doing as of now. These things were not possible before due to the two main problems. As Jenson said, one was the sequential training time, the loss that we were having due to that. So what was happening was we were having good hardwares, good GPUs, but as the data was processed sequentially, we were not able to harness the power of parallel computing. That was the first thing. That was the big problem with LSTMs. And as we all know, the problem with RNN was the short dependencies. Like it was unable to capture the long-term dependencies that were present. So if I ask you all to answer this question, is my screen visible? Is the screen visible?
Yes, yes.
Okay. So if I ask you all to answer this question, uh, I just need count how many of you think what the option will be. You can unmute yourself and answer. What you all think? What the answer for this sentence will be? Sorry if I have made some spelling mistake, but what do you think? If you think in a way a machine thinks or a machine model thinks, what do you think he will predict the output of the last thing? You can speak.
French, I guess.
Okay, so I got one vote for French. Anyone else?
Option
Anyone
A.
supporting Chinese?
French.
French 3, okay.
Option A.
Any option A, French, okay. Anyone else supporting any other option or asking ChatGPT as of now? No one is supporting Chinese as I see here. Is there anyone who is saying option B or option C also? You can unmute guys if you want to. Okay. Yeah. Something- yeah, Kedar. Your mic is unmuted. What do you think? What is the answer? What do you answer? Hello, Kedar. Or might be too. Okay. So the thing is, you all are correct, but you are wrong at the same time. If you see this sentence, the sentence says that you live in France and you love to eat Chinese. It doesn't say that you live in China or any other country where the language which spoke. So the answer for this would have been French, correct? But if I ask the same question as of now to RNNs or LSTMs, they will answer me as option B, that is Chinese. And the reason being is the short-term dependencies that we have. What this RNN will do is he will see well, he will give the highest priority to well, weightage to well, then he will see speak, then he will see can, then he will see I, then he will see Chinese. So here he will get Chinese and here little France. So if you see 1, 2, 3, 4, fifth word is Chinese, 6, 7, 8, 9, 10th word is the 10th word is French. So if you see, then the weightage that the Chinese word will get is more than the weightage that a French word will get. So the answer for this question by analysts and LSTMs would be Chinese. But if the same question are asked to transformers, I will get is French. And the reason being is attention. So that's the whole thing that we'll be discussing now. What is attention, how it works and everything. So what I will do is I will now go in passes. This is a big model. This is a big whole transformer, how it the way it looks. So we'll be explaining few things in it. I'll be going in passes. In pass when I will cover the overview. As I proceed the passes, I will go in more depth. Okay. So is my pointer visible? Is my cursor visible?
Yes, yes.
Yeah. So as you can see this, you can clearly see that there are two parts in this diagram. This one is this part and one is this part, correct? So if I say this part of transformer, this is a transformer architecture. This part of transformer is called encoder block, and this part of transformer is called decoder block. Now, if you stack encoders over encoders, you will get BERT, B-E-R-T, bidirectional encoder using that is made using transformers. And if you stack decoders on one of the above, you will get GPT, that is generative pre-trained models. As we have GPT-3, now GPT-4 we have. So if you stack this above one above the other, only this part you get the GPT, and on this part if you stack, you will get the BERT. So whole this complete thing is called transformers. Okay. Now let me give you some example how this thing works. Okay. Suppose here down I gave a sentence. Hi, my name is Shubham. My name. And my goal is to get this sentence translated from English language into some vernacular language. Let's suppose Kannada, okay, or suppose Hindi, okay. So what here it will be done is I can't write in Hindi, okay. Okay, I will write mera naam. So how this thing will be done is, see, here you can see input. Whole this sentence will be given word by word as an input to this transformer. Okay. Once you get this input, it will do positional encoding. We will be talking everything in very depth. Don't worry about that. After doing positional encoding, if I give you an idea what positional encoding is, just identifying the position of words where they are, which was missing in the RNN. RNN we were not doing positional encoding. That was one of the biggest problems that we are facing there. So here we'll be doing positional encoding. Then here this block, the encoder block, here we have multi-head attention. What is multi-head attention does is, it will look at the first word my, and it will pay attention to every other word in the sentence. Understood? Then it will look at the word name, and it will pay attention to every other word in the sentence, like my is Shubham. Okay. So in this way, attention is given to every word in this whole sentence, in this attention block. Then in the additional normalization, what we do is, we add a skip signal. This is called residual signal. This line that is going directly from here to here. What it is doing is, it is avoiding the vanishing gradient problem. What will happen is, see, as of now the sentence is very small, but if this sentence become a paragraph, then we might experience a vanishing gradient problem. And as I'm doing attention, so what will happen is, see, you suppose this is my, and after 1000 line I have written a word. So this my attention on the basis of that word, basically the relation between this and my and that word will be very less, because it is not even connected like that thing. Okay. So to avoid this, suppose I gave you a paragraph, okay, in which in the initially only I mentioned a place name, and everywhere in the whole paragraph I am just mentioning the place as a pronoun, it something like that. Okay. So you have to understand, and at the end if I ask you what was the place name, as we have did in a junior senior cases to find the answer of the question given an English paragraph. So at the end, if I ask you a question, what was the place name, then you must track the sentence and the initial thing also. So for that thing, we have to give multi-head attention. So after doing that, we have to normalize the layers. After doing that, we pass everything that we got to a feed forward network. The feed forward network does nothing, just it helps us to get the input that we got, to organize it, and to give it to the decoder part. So now see, as you can see, there are same blocks repeating everywhere. Okay. But here, if you see, there is a multi-head attention and there is a masked multi-head attention. Now see what happened. Here the sentence I gave. Here the sentence, as we all know, these machines don't understand sentence. To whole these 4 words will be converted into a vector. So it will be something. Here I will get a 4 vector like thing output. 1, 2, 3, and 4, something like this as an output. Okay. Now this whole 4 vectors will go into the decoder block. Okay. And as you can see here, there is something coming from here also. Okay, then what is this coming from here? So while training a decoder, what we do is we give a starting tag, start. Okay, what it indicates is that you have to start taking the things and you have to start converting. Now see what will happen. This 4 vectors will go here. It initially has nothing, so nothing will be done here. And I will, as I'm training it, so I will map it to a single word. So the first word will go here. The first will be mapped to a mera naam, mera. Okay. Now what will happen is that mera will go here in the input. and the other will come, other word will come from here. So mera is coming from here, the other word is coming from here, and the same thing is performed. The mass multi attention is taken into place. The feed forward touch and the activation functions are there, and at the end it will predict naam. Then the naam goes here again, and the other word comes. So in this way, whole this thing works. Is it clear? This much? If this much is clear, the basic idea, the basic overview is clear as of now. Is there any doubt in the basic overview?
Shubham,
Yes.
can you like maximize the screen?
Okay. Sorry. Uh,
Yeah.
yeah. Is the idea now clear? Is the initial idea, the intuition behind transformer is conveyed?
Hello.
Yeah.
Could you explain this output embedding part once again, please?
Yeah. See, I will, as I go in depth, I will explain every part of this position, this everything code. I have wrote the code, so every part of this will be explained very deeply. Just what I want to want from you as of now is, did you understood what the input is, how the output is? Is that much thing is clear?
Yes.
Okay. So what I will do is now is I will explain you some initial things that are needed to understand transformers, some basic terminologies that we need. Okay. So transformers. This is architecture, as I said, architecture of the transformers, the encoder part and the decoder part. Okay, so one important that we should know, these are the importance that we should know before starting with transformer, is one-hot encoding. What is one-hot encoding is just representing a word in a vector format. So how this thing is done is, what we do is we map every word that is available with us into a vector dimension space, a word dimension space. Okay, you can imagine the space as a space is a graph in which every word is there closely to the words that are related to it. Okay, and then we gave them a one-hot encoding. Okay, so this is in this is where we give just see files find my. So if I want to write this sentence, how it will be, find my file. So it will be one. So it will be 2 3 1, something like this. Okay, the second value, the one is in the second place, the one is in the third place, and the one is in the first place. So in one encoding, we just represent that words by putting one, and baki another array we put 0. Okay. Now dot product we all know what dot product is, so not wasting much time here. The matrix multiplication we all know. These are basic things that are required because all these things are happening there. Now comes the first order sequence model, the Markovian model, as we can see. So as you can see here in the whole sentence, show me my file please, show me my photo please, show me my directory please. So suppose what you're doing is you're making a model that can predict the next word. So if you're giving this sentences, show these 3 sentences into input, just these 3 sentences are input. So what your model will learn is, after show every time me will come. As you can see, after me every time my will come, but after my there is some probability associated with it. The maximum times you gave this, if suppose you gave this 3 sentence only 1,000 times, and maximum times this my show me my photo was there, so it will give the highest value to my photo thing, then my files, and then my directory. Understood? So in this way, the first model sequencing is done. Basically, only this one word is found on the basis of the my word that is present there. Understood? Like if I want to find which word is there, which word should come here, I will just see my training data set, how big the training data set was, and how many things are involved in it, and I will just see the initial word before it. Only the my thing is giving without. So this whole thing we can represent this in a matrix transition thing, the matrix transition model. Okay. So as you can see here, this directly everything written here, all the words that we have in the vocabulary. So as you can see here, there are only 7 types of words that we have in the vocabulary: dictionary, files, my, me, photo, please, show. So we wrote all the 7 words like this, and what we did was we gave what word can come after the next can be the next word of this word. So after that is please can come. Please came. Okay, so we gave it 1. After files, please can come. After me, my will come. After my, this probability, only this line you see, 0.2, 0.3, 0.5. All the others are 0 or 1. That is, they are very confident or they are not confident. But after my directories can come, after my files can come, after my photos can come. And it was depending on the data set we use for training. So this is the first sequence model. That is just looking at the word my, I will predict the next word. Okay. Now comes the second order sequence models. What is happening here is, if we read these two sentences, check whether the battery ran down, please. Check whether the program ran, please. So as you can see here, if I want to predict the next word after program, sorry, after the, then it depends on the battery. Battery. If it is battery, then I will take this path. Battery ran down, please. Okay. And if I want to just, if I just want to see a program, then it will be the program ran, please. Okay. The downward will not come in this path. So again, the dependency of please, of the word please, is depending on two things: the ran thing and the word that was taken here. On the basis of this, the middle level will be predicted. Understood? So what we did was, we said, instead of doing this, putting only single words, what we can do is we can put two words: battery ran, program ran down, ran place, like this thing. So to get more good results, okay, battery ran, to get the dependencies, okay, basically dependencies of the previous words. Battery ran, check whether program ran, the program ran down, whether the. So here we got all the priorities C. Here, if you see here, there are some things which got decreased. Here if you see ran 0.4, 0.6. Here it became 1, directly 1. So the complexities got reduced. But at the same time, there is one more issue which arises. If suppose, as I said, you have wrote a whole big paragraph, okay, and the word is not dependent like just 2 words back or 3 words back, it can see and predict the thing. If it is more like 1,000 words back or 2,000 words back, this whole metric, if you imagine it will be 1,000 words written here, then this matrix will be so big that it won't be computationally possible for us to compute things. Okay, so there we introduce skip, second order sequence model with skips. What skip does is, skip basically skips the word that are not of importance. Okay, so if you see here, down and place, there are arrows highlighted. The dark arrows that are highlighted has more weight than the lighter arrows. So what these lighter arrows are, basically we call them as skip connections. We added them as a skip connection. So we will skip that connections. Okay, that was that. Yeah. So after doing that, the whole skip connection, we got things little more clear. It was more steady, more down. We'll see this in code as you go. Now the biggest issue that we face. This is the issue. Can everyone read this? Can everyone read it? So if you see, I gave a Google Translator. I gave this Google Translator this. Fried eggs should be properly cooked, and if they are frail or elderly people in the house, they should be hard boiled. So you can understand what I'm saying. Here I'm saying if you have old people or frail people in your house, you should hard boil the eggs. Okay, but see what the translator did, what the Google Translator did. It says तले हुए अंडे अच्छे से पके होने चाहिए, और अगर घर में कमजोर या बुजुर्ग लोग हो तो उन्हें सख्त उबाल कर ही खाना चाहिए. So it said कि you have to cook the old people, okay, which is wrong. So this is the problem, because here initially I gave the word and I called the dependency here. They should be hard boiled. So it didn't understood what I'm speaking about. Whether I'm speaking about this elderly people here or the fried eggs here. The dependency became so less that even the Google Translator failed. Understood? So now this problem that we face can be solved using transformers. If we use transformers here, it will be easy for us to get good results out of it. Yeah, so it's a fun thing. Like it should have not have been happened with Google Translator at least, but yes, it happened. Then comes the masking. Masking, what it does is it basically put some words, it basically stops some things from saying. If you see here, what I can do here is I can mask some words here to put this dependency directly on this word, they and fried. If I would have did this in my model, I would have got correct translation out. But as this thing was not done here properly, masking was not introduced here properly, this the output that we got was not that correct. Okay, so masking is basically masking some of the words. Okay, this thing masking is very important in the decoder part of the circuit of the transformer. If you see the transformer here, as I said, I gave the one word output and I gave that only one word as an input. I don't give the whole sentence as an input to a translator system. Even if I have the parallel data, the parallel English sentence, the parallel Hindi sentence, I won't give whole Hindi sentence here. I will give the English word, I will give the previous Hindi word, and I will try to predict the next Hindi word. Understood? Why I'm doing such thing is to basically make my this decoder part learn how to give the next word as output. Understood? So masking is very important in decoder. As we see in the codes, we will see there how masking impacts the output of the yes. So this was the thing. Yeah. So we talked about masking. We talked about masking. So how to improve masking? Basically, put every other words that you think are not required by you 0, and the only words that are required by you is 1. Multiply them, so you get the final masked output as a output. So it is as simple as that, as a simple intuition as that. So after doing masking, this thing is what we get. Initially, the thing that we had was this points where there's 0, 1 more there, like this something. Then we came to this by having second model dependencies, having 2 words involved. So, but after doing masking, we just came in this thing. So as you can see here, battery ran down. Please will not come here. Program ran, please. In this way, it gave the correct output to us. Yeah. So now let's talk about more depth with coding and with drawing how things are working. So let's now start with the transformer thing. Is it clear till here? Is it clear till here? Is the intuition behind everything is clear till here? Hello. If you have any doubt, anything regarding it, you can ask. Is anything any doubt? Okay, I assume as no one is asking, there might not be any doubt. So now going ahead. Now what I will do is I will simultaneously show the code also, and I will simultaneously show how this code is working. See, first we will look at this. What is attention? We will understand what is attention, what is self-attention, what this block exactly actually does. See, what was happening as of now is we were giving a Hindi sentence to it. The Hindi sentence was converted into an embedding. Basically, we were converting into embedding. Basically, cannot nothing but represent the whole word, a whole sentence in such way. Mera naam, so I will first Mera will be 1, and the other things will be 0. Oh, sorry, my name is Shubham. So for my it will be 1, others will be 0. For the second thing it will be name will be 1, and the other things will be 0. Only that thing we did here. Then we added positional encoding, which I'll be explaining down. And after doing positional encoding, we gave this to multi-head attention. Now see what multi-head attention does. So multi-head attention, what it does is it has 3 things in it. It is Q, K, V. Q is query, what I am looking for. K is the key, what I can offer you. And V is the value, what is actually offered. Okay. So now what I'm doing is, as I wrote a sentence that was this. Just clear this out. Yeah. So as I wrote a sentence, my name is Shubham. So it contains 4 words. So that's why I gave L is equal to 4. That is the length of the sentence I have is 4. The DK and the DV are the key and the value vectors, which I assigned 8 and 8. Okay, as of now. Now what I'm doing is I'm randomly assigning any values to them, and I'm printing this. So as you can see this whole thing, it contains this first thing, the Q. It contains 4. First of all, 4 things. Okay, four vectors. Okay, the first vector corresponds to the first word my. The second vector corresponds to the second word, that is name. The third vector corresponds to the third word is, and the fourth vector corresponds to the fourth word is Shubham. Okay, this is how the Q is made. This is just random values that has been initialized. Okay, why we give 8 and 8 only? So see, the vector dimension can be very large. Okay, in the paper it is 10,000. Okay, but just for the sake of demonstration purpose, I'm giving it 8. So what it means is I'm basically having just a 8 dimension word representation available with me. Okay, so I printed Q, K, and V values. See, so it will printed. Now what I'm doing is the formula. What it says, you have to first understand the formula. What formula of attention says is You have to multiply by query what you want into the key what you can give, transpose upon underscore dk, and this dk is nothing but your variance of the whole thing. Basically we are doing this thing to basically decrease the variance of the thing. Like it must not vary, the attention must not very high, it will be very difficult for us. So if I perform this operation np into multiplication of q into k dot t, that is k transpose, so I get this four values output. These are the four vectors representing this whole words that I have. Okay. This was the variance. Why I did denominator was because I wanted to decrease the variance of it. The variance now got to 1.47 and 5. It got decreased. Okay. So sorry, point 0.5 is there. So what I did is I scaled it down. So scaling is this thing. This is the thing that I got underscore divided by underscore square root of dk. So when I did this, as you can see, it was 5 here. The variance was 5. The variance came down to 0.71. So here we are doing this thing. Okay, we are scaling it down. So that's why that thing is needed. So I got finally this whole four vectors representing my this sentence. Okay. Now comes the masking thing. I will explain as I go ahead. So what I did is I just made an array of 4:4 representing my this sentence. Okay. Now what is happening here is, see, I put all the values above the diagonal as 0 and all the values below the diagonal as 1. If you see, what I mean to do here is, if I write this sentence here like this, my name is, so if I give this sentence to a decoder only knows first, initially it will know nothing, then it will know my, okay, then it will know, it doesn't know what the next word is. 2, 3, 4. Next time it will know name and my name. It will know my and name, two things. Name. It won't know the next two words what they are. So to represent this, what I did is I added 1 for the thing that we know and 0 for the thing that we don't know while training. Okay. So this was done, and then to basically to fit in the softness function, what I did is I made all ones as 0 and all zeros as minus infinity. So after doing this, I added the scaled value that I got, the scaled value, this value that I got, plus the mask value that I got, this thing. So after doing this, I got this array. Okay, what this array represent is, this array represents what is coming out from this multi-head attention. Okay. Now what I will do is, I will, for just the sake of simplicity, I will add I will just apply softness function over it. After applying softness function over it, I will get this new array. Okay, and this was my previous array. So as you can see this, if this was the initial things that I gave to it, this was the initial difference of the sentence I gave to the multi-head attention block, it paid attention to the every word with corresponding to the next word or the previous word, and it made this thing out. This thing contains the context of the sentence. Context of the sentence means Shubham is there, so name might be there. My name is there, so my something like that. Some context of the whole sentence is retained in this thing, as our brain does. Okay, so this is a new array that we got, and as you get this output from here, that will be passed to normalization thing. So this is called attention thing. This is what attention we did. Is this much clear? Is this much code and the diagram is clear? Am I audible? Is that much thing clear?
Yes.
Okay, so now going ahead. Now I just put everything in one function that can be run. So if you run this function, it will be done. It will be done here. Now coming to multi-head attention. Now we just talked about the attention, correct? There was only one array and only one thing. There's only one sentence. We were only making one array, but it doesn't work that way. What we do is, one array means, what I did here was I just took my and I just found my dependency on the basis of name, is, and Shubham. So what we have to exactly do is we have to pay multi-head attention, like attention of my on the different word, attention of name on the different word, attention of is on different words, and attention Shubham on different words. Okay, what we did here was we just used my and we paid attention on the basis of my to the every other word. So now we will do is multi-head attention. In multi-head attention, as you can see this, there is this. I will explain this whole thing. Suppose there is this, I have a whole vector converting everything into a vector. If I have a 5 and 2 cross 1 vector, okay. What I will do is I will divide that 5 and 2 cross 1 vector, this vector that we had, this in every single vector that we had. this every single vector that we had, that was representing our one word of the whole sentence. So if one vector that I have, I will split that into KQV vectors. This 5 and 2 is initially described in the paper, the transformer paper, because they have fixed the big sentence that we can give in it. So it will be divided in three parts, K, Q, and V. So as you can see here, 5 and 2 will be copied three times. So it will be 3 times 5 and 2. And this thing, K, Q, and V, will be made 8 part. I will make its 8 parts. So it will be 64 times 8 converted. Okay, so Q will be 64 times 8. Okay, in this way I will do for K also, and I will do for Q also, or V also. And for every word I will do this thing, and I will pass all this thing to the attention unit, and attention unit will get other output, other KQV also from other words, from my for name word, from each word, from Shubham word, and it will pay all the attention to it. It will concatenate everything and to give this final metric to us. Okay, so as you can see, this my final metric here. This final metric, as you can see, it contains the words and the probability of the words, but these probabilities are not 1, 0, 0 like that. They contain some values which are other than 1 and 0. So this have attention of what the next word might be. So let's see what is happening here. My, it has maximum probability of here my. So the first word is my. If I see the next word is name, which is having the highest priority. Then here it says Ajay. Now see, here it is given problem. My name Ajay is saying. He is not giving attention to is. If we only look towards if you only look to this row. So why this is happening is, this is because we have not did positional encoding here. This positional encoding we have not included as of now. If we do a positional encoding also, positional encoding is nothing but it knows the position of word that appear in your sentence. So if you do that also, it will get corrected. As we go down, we'll see. So what I'm doing as of now here is to code all these things that I spoke. I have a sequence length of 4. That is, my name is Shubham. The length is 4. My batch size is 1. I am just for demonstration purpose using one batch size. My input dimension, output dimension is 512, 512. That is given in the paper. It can be decreased as of now also, but let's keep it 512, 512. What will happen is, other things will be padded. Like if suppose I give 10 values, if I give 10 values, other things will be padded by some random values, some average values, so it will be understood by the transformer. It won't take accept that thing, and it will train only on this part. So I did 3 times, as I said. Everything has to be divided in 3 parts. The 512 will be divided in 3 parts. As you can see, the 512 is divided in 3 parts, and the KQV layer is made. So the new dimension of the KQV layer is 1 cross 4 cross 1536. That is, one row will have four things, and it is divided in 1536 because 512 times 3. Okay. This is a distribution of how it is. It is not as of that much importance. Now we come here. So what we did is we divided it into heads. As I said, we'll divide it in 8 parts. So now our whole thing is, we have 192 KQV for every word. We have made 8 heads for it, and such we have 4 words. Okay. So after doing this, we just rotated this array basically. So we got 184 192 because we need this thing in our further process. So after getting this thing, what is important for me is this dimension 64, because I want to train my whole KQV in such a way as I did above, as I did here KQV, same thing I have to do here also. So for that thing, I am converting my dimension. I am taking my dimension that I got 64, that is 500 divided by 3, then dividing that value that came out by 8. So this thing will be given to the multi-head attention block. The multi-head attention, as we did above, everything will be same. All the inputs that are given here are same as we did in the single head attention. And similarly, you will get this thing output for the 4 things that we have. So now what we got here is the mask of the only first thing, the mask of the my only the my thing we got here. So this is because 0, 0. In this way, you can get for 1, 0, 1, 0, 2, 0, 3, and 0, 4. So whole thing you will get for whole mask for everything you get, because it is multi-head. You paid attention by word on every other word. Is that much clear? Is this much clear? It is a little tedious to understand, but yes, it is what is happening inside. It pays multi-head attention, like every word pays attention to every other word appearing in the sentence. That's why we have this thing. And initially that we did was just attention. We were only having this one word, and we are paying attention to the other words happening in the coming in the sentence. So I made a multi full function here that can be directly used by you. Now one thing that is worth seeing here is, wait, I will run this. Thing. One thing that is very worth seeing here is, okay, just a second, please. As you can see here, I have wrote mask equal to none. So this thing is done for encoder. As you can see, there are multi-retention for both the encoder part also and the decoder part also. Just a second. Yeah. So I was saying, as there are multi-retention for both encoder and decoder, but as I said, the decoder must not know what is the next word, because then it will be cheating. It won't learn nicely. Because if you know what the next answer is, you will always give the answer now. What decoder was doing was, it was getting the word that is to be printed, the English word. It was getting the previous Hindi word, and on the basis of this two, it was printing the correct Hindi word as of now corresponding to that English word. But what if you know the correct Hindi word before only? What you will do is, you just fit that. You will always give that dimension the maximum value. So to avoid that, we here do mask multi-attention. So what is happening here is, see. As you can see, observe the output. The output here contains, we'll see just this. See, here the output contains 1000, correct? But if I add if I add mask here, what happens? See. It will change this values here. These values were not initially zeros, but now this values has been changed. This values became zero because I added masking in it. I masked the next word that is to be that was known before in the encoder part. Because in encoder you must know whole sentence. The whole English sentence is to be known. To train this thing, to understand what is the position encoding in it, how the position context of the sentence is, to understand the contents of the sentence. But in conversion, but in translation, you should not know the correct Hindi word directly. You must go through the whole this process. Okay, so now that whole thing is implemented in this, and it was running this. Okay, now coming to the position encoding thing, is this much part is clear? Is this much part clear? The multi-intention and this part is clear. How, why we need mask and why we don't need mask here? Is there any doubt as of now? If you have any doubt, you can ask. uh, okay, so no one is
No doubt.
asking. Yeah, no one is asking any doubt, so I will move ahead. If you have any doubt, please ask. Transformers are a little tedious to understand. These are big architecture things that have been there. But yes, if it is worth understanding because many things are going. Now let's understand position encoding. So now what we have seen is, we have seen this multi-retention. We have seen input embedding, and we have seen mass multi-retention. Okay. Now we have to see one more thing, that is position encoding. This thing was missing in RNNs. This thing was missing in LSTMs. Okay, it was present in some fashion. It was not helping RNN or LSTMs in the way it helps the transformers. So now let's deep dive into what we have. We have our name, we have our whole sentence. What we did was, we padded, as I said, this transformers architecture takes input of 512 come across the 512 thing inside. But as if suppose our sentence is small, the other thing will be padding that will be given to it. So this is a max length into max length that is given. The whole thing is given. This thing is added with the positional encoder, and after adding to the positional encoder, we get this thing as output. This x is this, here we get this x, and then this x goes into the multi-retention. I will again repeat. We have this English sentence. The English sentence will be converted to its one-hot encoding. After converting it into a one-hot encoding, this will be added with the position encoding. After doing position, it will be done with input and embedding, then the position encoding, and after doing that, we will get the x. The x will go in multi-retention. This x will go into multi-retention. And as I said, this will be divided in 3 parts. These 3 arrows shows the 3 parts, the K, Q, and V, which will be given to the multi-head attention here. Okay, so this is what is shown. The input, the sentence that will given, the here we get the X, then we add the position encoding to it, and then that X dash is going to the multi-head attention. So we divided K, Q, and V, Q, K, and V. And this Q, K, and V is further divided, see K, Q, and K, K, Q, K, Q, and V, K, Q, and V. So it is, everything is converted thrice. Every vector is converted, copied thrice. Okay. Then the thing comes is, what is positional encoding? Why we need positional encoding? So positional encoding is nothing but it's helping you to understand what word was there before before a word, before that word, and what is what next to the current word that you are seeing. So in the paper, they use very simple functions for doing positional encoding. They just use sign and cause. Okay, if it is becoming a little difficult to understand what positional encoding is, I will give you an example. So positional encoding for my will be 1, for name will be 0, 1, something like this, or 2. If let's keep it simple, 2. For the name, for my name is will be 3, and for Shubham it will be 4, something like that. But not as straight as this. It was done in this fashion. The position of the word, here the formula is the position of the word upon 2 to the power I. The I is the index value, and the d model is the model that the dimension of the model that is there. So our dimension was 512, so something like that. Okay. So what we'll do is here is we will, and one more thing. Even positions we will get from sign, and the odd position we will get from cos. Okay, where I is odd and I is even. From this function we'll get the positions of odd words in the sentence, and here we will get the even. So what we are doing here is we are arranging till 0 to dimensional mod. So we had only we had only 4. Correct? My name is Shubham. The length was only 4. So dimension of our this thing is only 4. So it is arranging 0 to 4, skipping every 2. Even it is, and here we are doing thing. We are putting this formula. So the formula is 1000 to the this only this denominator we are treating 1000 comma even the even value that we get, every even value that we get, upon d mod, that is 4. So we get this as an even diameter, a denominator. Okay, same we do for odd we get this as a this as a denominator. And after doing this, we, as you can see, this one thing is, you can notice one thing, the even denominator and the odd denominator here are same. Okay, so they come out to be same. Okay, so that's why what we are doing is we are saying denominator will be equal to even denominator, or we can take odd denominator also. Okay, so now we are implementing this whole big formula, that is position equal to torch.arange max sequence length. That is this position we are giving in, and reshaping the sequence in comma 1. So we get all these positions 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Here if we give a big sequence, here we give a 10 sequence. Okay, here the name was only 4, but here in sequence we give 10. So if it was confusing, so it is a 10 length sentence. It is something of length 10. Okay, something like this. It is 10, 4, 5. So that's why we got here 5. Okay, 5, and here we got 4. So don't confuse with it. Yes. So after doing that, we perform this formula, torch was sign position upon denominator, cos position upon denominator. After doing that, we give this even position encoders and the odd position encoders. This represent, what this represent is the input sentence that was given by me, and the after putting the one not encoding over it, the sentence when we want to represent, when we want to give it some positional context to it, giving a positional context of a word in a sentence. We have done this. So it gave a positional context to a word in this sentence. So as you can see this, now we got the positional encoding from here. Now what we'll do is we will add this positional encoding with the one hot encoding that we got, and that complete will pass here. As I said, as I shown in the diagram, this X is what we get from one hot encoding. Okay, and this position encoding that we got now, this position encoding. Now we will add this whole position encoding with that X, and we will pass it to the multi-attention. Now one more thing, This is for even position words, and this is for odd position words. Now what you have to do is you have to concatenate them, because we have to at the end give finally the whole sentence. No. So what we'll do is we'll concatenate them. So as you can see here, we stacked them up and then we flattened them up. So after flattening and stacking, you can see this became the first, this became the second, this third, this part as fourth, this as fifth, and this as sixth. So this is what happened in this first row. Okay, and in that way the whole thing is represented. The whole thing was given a position encoding. Is this much clear? Do you have any doubt in this much thing? Is anyone having any doubt? Okay, so as I see, there is nothing, no doubt. So one thing now to say, now you know things how they now you know very many important things of transformers, how this transformers basically work. You know the encoder part of it, you know the decoder part of it. Okay, there are same things repeating here: multi-attention. The feed forward network is just the simple feed forward network. Okay, the only thing that we need to understand is what is this add norm, what is add and norm, what is this doing, and why there is a residual connection over it, why there is a skip connection over this. So now let's understand what these things are. Going towards the layer normalization. So suppose this is your feed forward network. Okay, your feed forward network X output will be given by function of WTX plus B1. This is a normal feed forward network output, correct? So what we do in layer normalization is we normalize the output of this layer, whole layer, by performing something like this. We take the output, we subtract the mean, divide it by standard deviation, multiplied by a parameter that can be learned plus beta 1. These both parameters are learned as we go for each and are same for each layer, and as we propagate this parameters are learned. So this thing is called normalization. This is called normalization. And what is adding, what this word add here means is this skip connection. As you can see, this skip connection is added to the output of this thing. So in the normalization, after the normalization that we get, we add the skip connection out, this x that we got, the initial x that we had, this x that we were adding to position encoder. After position encoder that we were getting this thing x dash, which we were giving to multi-retention. At that x we add directly to the add and normalization thing. Okay, so as you can see here, the same code is this is thing how code is running. The B here stands for the batch size. Don't worry about it as of now. You will understand as you go ahead. So here the important things are gamma and beta. This is gamma and beta. The gamma and the beta, that thing have been given here. So gamma and beta are ones and zeros, which has been made, and that thing we have calculated the mean of the whole x that was given to it, and the weight standard deviation of everything, and we subtracted and we found out y. After finding out y, we found this out. This out was gamma into y plus beta, and then we got this out as output. So this was the addition normalization parameter. So if you see this before, if I see, so this was the output. Okay, this was the thing that was coming out from multi-retention. Assume it is this thing coming out of the multi-retention. Okay, 21.3511. But after doing everything, after performing that thing, what we did is this. What happened is this is something that is coming out like that. So 0 minus 1 1. So it is normalized in that range. Okay, that is what happened to it. So normalization was done here. Is this much part clear? Is normalization part clear? How normalization was happening? Is there any doubt with anyone? Okay. No. Yeah, so that was the normalization part. So this ends the coding part of it. But wait, I will explain this everything once again to get you again back, because it is little tedious. I know you can. So let's again see this whole transformer. What is happening here? Input sentence is given to it. Input embedding, one out embedding, it converts this whole sentence into a vector 1000 0100, something like that. Okay, positional encoding, giving a positional context to the whole sentence. If this was the whole sentence I had, I have to give this some positional encoding. Okay. So that sentence that you remember, I asked the question, the French, the Chinese, that thing. That thing was differentiable due to two things: the multi-tension that was there and the positional that was there. So positional encoding is giving positional context to the words, after which word is coming. So giving some positional context to it. Okay. The output that we get from here is divided in three parts: the query, key, and value vector. Okay, and then it is given to the attention block. Attention block formula is q times k to the power t, k transpose divided by underscore dk. Okay, under root dk, and the value that we get out of it is multiplied with the value vector, with the value kqv, the value vector. So assume this. What is happening here is imagine this how it is happening. You have a query, you have a key. Query says what I'm asking, key says what I can give, and you have value vector. Okay, so you take query and key, what I'm asking, what I can give, and multiply it. Okay, decrease it variance, and then you multiply it with the value vector. Okay, so you get key, what is the value of the thing, what was the exact word. So you learn the exact word and output here. Okay, and after that, this script connection and the output that came is passed to the addition normalization layer. What normalization layer does is it normalizes every layer, every output that came out, and the addition thing, what it does is it adds the addition of the weights that were initial to provide the problem of gradient to variation gradients. Okay, and all this thing is going to the feed forward network. Feed forward network basically learns how to connect what vectors belong to what vector belong to what word. It basically learns that again addition normalization, and this whole input is given to this. So after this thing completes this connection, what it contains is it contains the vectors of this word, the vector of my one vector, the name is, and the is and Shubham. So basically, if I say actually these are not complete four vectors only, that they are divided into subwords using byte pair coding encoding. Why we do that is because if we consider whole word, it might become very big. The vocabulary will become very big. But don't go in that depth. So what we do is basically we get four vectors here. Okay. Now assume what is happening here is I will take first vector, that is my. I will pass this my here. Okay, in this decoder part. Decoder initially has nothing. Okay, so my goes here. Here the my comes. The decoder only understand that my has to be plotted with the word, that is mera. So the my word weight and the mera word weight are aligned, and we get the output mera. Okay, it is basically predicting a handwritten digits. You might have done handwritten digit recognitions. In that handwritten digit is written, we just scan that handwritten digit, you give to the feedforward network. It creates a flattered layer, and the neurons that fires give out the output. In similar way, feedforward network, what he will do is it will take that word mera vector, my vector, and it will take mera vector and it will plot it. It will connect it. So we'll get the output mera. Now what will happen is that mera will be given again as an output embedding. So mera will come here, the position encoding will be done, and here the mask multi-retention is there. Mask multi-retention is because you don't know the next word out about after mera. Okay, you only know the English word, that is name. So what here will go as input is mera and mera vector, the mera corresponding vector and the name corresponding vector. So it got name and mera. After that, he here pays attention to all the things that he got. After paying multi-rate attention, it gives the feedforward network. The feedforward network then plots the name to the naam, and then you get mera naam as a naam as output. Then you passed mera naam as input. Did you understood? Is this much part understood clearly? Hello, is there any doubt? Okay, so now I will explain how basic of ChatGPT is. Okay, as I said, only the decoder part is ChatGPT. So what it does here is you give a prompt to it. Okay, let's do with ChatGPT only. So what it does here is this all word, as you can see here, how it is writing this. Okay, what here it is doing is for predicting every word, the every word that is he is writing, it is taking all the context of the everything that it was written, that was written before, and it is giving that whole thing into it. Okay, and this whole decoder part is stacked one over the above to predict everything. See, I gave a prompt to it. This whole prompt went to the encoder. The encoder understood the prompt. The encoder gave the prompt to the decoder. The decoder part understood what is written and it started giving output. Every word was given output and it was given back. That's why we can see that cursor coming again and again. That is just for UI, but in the backend, it is happening in such way. Every word comes, it goes back. The word comes, it goes back. In this way, the whole thing is computed. So as you can see here, even the transformer says, after computing the context vector and applying self-attention, the decoder passes a resulting representation through a feed-forward neural network, which is here, which produces a vector of logics that represent the probability distribution over vocabulary. So what came output from here was a 5 and was a 10,000. The paper has 10,000 space. Basically, the dimension is 10,000. So a 10,000 big 1D array, in which there might be some probability, high probability, that gave you this word. This every word came out from there. Okay. So is it clear as of now how this all things work? Is there any doubt with the transformer part? Anything like any difficulties or anything not understood yet? You can unmute and ask. Okay, so it seems that there is no doubt. So I will stop sharing. Yes. Now, yes. So this was what we did till today. I'll be recommending you all to please go search about transformers, to please learn about more about transformers, the RNs and the LSTMs, to get all the concepts clear, what we taught you as of now and what you know beforehand. So it will all get settled. And tomorrow we'll be having session on stable diffusion in GANs. Basically, we'll be learning there how we are going to make images. So that's it from our side for today. If the session is open to ask doubts and ask any query regarding this session. So if you have anything, you can ask.